So we're going to be taking a look at an introduction to sequences. Probably going to need a couple of days to cover all the basics that are in this introductory section of the chapter, just because there's so much vocab. Hopefully you feel like in the end the mathematics is pretty straightforward, but we're going to be talking about the fundamentals of sequences of series, factorial notation, sigma notation, the difference between an explicit or general term and a set of recursive formulas. Ultimately, in the next section, take a look at arithmetic sequences. And in the next section after that, 8.3, geometric sequences in series. When I am at the end of Calc 2, teaching the last and hardest chapter, arguably, of that particular course, the foundation. At the end of Calc 2, we are reminded that it's very hard to integrate, especially integrate, but take derivatives and integrals of functions. And a lot of functions cannot be integrated. And fewer functions, but still there are other functions that you cannot take a derivative of. So it becomes beneficial for us to be able to write polynomials that act like other functions over some interval. So we can make polynomials that act like logarithmic functions, base e exponential functions, sine waves, and so on and so on. That math has a very, very strong foundation in geometric sequences and series, specifically the geometric series. So even though we're just in pre-calc, when we look at what arguably is a fairly simple idea, part of the content we're learning over the next 3 days ends up becoming a very, very important foundational topic for the end of Calc 2. So all of this stuff continues to get recycled and built on as you go through mathematics until, ultimately you stop. I mean, people that do a liberal arts degree, like for example, don't need Calc 2. But if you're going to go into like engineering or pure mathematics or an actuary or higher finance, all of this will matter at some point in your career, or at least education. So what is a sequence? It's just simply a function whose domain is the set of positive integers. So if I want you to say, as our first example, what is the graph of f of x is equal to 1 over x? This is just a function. So what does the graph, okay, let's start with this. What is the domain of this function? This is a function, not a sequence, but a function. F of x is equal to 1 over x. It's a parent function. We talked about it, I don't know, chapter like 1 or 2. You can't divide by 0. So the domain of this is basically, x is all reals except it cannot equal 0. So we only have to eliminate one numerical value from this function, and that's its domain. This is a continuous function everywhere except where x is equal to 0. And where x is equal to 0, we have that vertical asymptote. And without scale, as x gets larger, what's the overall value of this fraction become? Smaller. And when x is really small, then this becomes really big. And a positive number divided by a positive number is positive. So we get this reciprocal function that has a graph that looks like, well, this. Okay? Graph the function. Well, if I change this to graph the sequence given by the general term, I'm going to be defining a general term and recursive formulas here in a minute. But graph the sequence defined by a sub n is equal to 1 over n. If you were to make a t-table, n would be, what's the domain of a sequence? Whether it's finite, where there's a set number of terms, maybe 5 terms, a sub 1, a sub 2, a sub 3, a sub 4, a sub 5, or an infinite sequence where the list never stops. If you were to make a t-table, what would be the values of n? What are your positive integers?
1 and 2.
Yeah, 1, 2, 3, 4 if you wanted to keep going. And you would have 1 over n, which is a sub n, is going to be 1 over 1, which is 1. or 1 over 2, or 1 over 3, or 1 over 4. And when you graph that sequence, I can kind of use the graph of the function as a guide, but what I'm going to be graphing is not a continuous curve or line. It's just going to literally be dots. And in calculus, which we're far from the end of Calc 2, but there's some benefit when you can come up with a function that acts exactly like a sequence. But at any rate, I can take the graph of this function, f of x is equal to 1 over x, and remove, well, the whole left side, because the domain of a sequence is positive integers and there won't be any negative numbers at all. But I want you to realize that the difference between graphing a function, as we've done all year, and making a graph of a sequence is the domain of a sequence is positive integers only. All the numerical values between 1 and 2 are not used. You know, there is no 1.01. It's just n is 1, n is 2, n is 3, n is 4. Make sense? Now, if I want the, as another example, if I want to write the first 4 terms of the sequence defined by a sub n is 1 over n, which arguably we just really did, we would be looking at a sub 1, a sub 2, a sub 3, a sub 4. And what is in the lower right-hand corner of this sequence notation? N. So when you write out a sequence, like maybe this is called sequence A, and the lower right-hand number, those are your values of n. So when you see a sub 1, a sub 2, a sub 3, a sub 4, you're being told you need to realize that that means that n is 1, that n is 2, and n is 3, and then 4, and so on and so on. And of course, we already have made a t-table, so we know that a sub 1 is 1, bless you. A sub 2 was 1/2, and then a sub 3 is 1/3, and a sub 4 is 1/4. Now, this is called a general term. If I want to know the 100th number in the sequence, if I want to know what a sub 100 is, well, a sub n is 1 over whatever n is. And if I say I want n to be 100, then the 100th term in this sequence, this is the first term, the second term, the third term, the fourth term, and that's going to go on for a finite or infinite number of terms. If I want a sub 100, well, then it's just 1 over 100. So there is the idea of a general / explicit term, which is a sub n is written and there's some kind of expression in terms of n, like we just did, which arguably is quite simple. Okay, next one's going to be even simpler. If you want to write out something called a set of recursive formulas, that is going to be something like where you have a set of recursive formulas in general are going to be 2 formulas. And you're going to be told that, it doesn't have to be, but usually the first term is some number, some value, some constant. It doesn't actually have to be constant if you get really abstract problems, but at this level it will be. We're just being introduced to this. So a sub 1 usually will be given, and it's going to be just equal to some number. And then a sub n, so not a specific value, just any number in the list, can be found by taking some other number in the list. Most commonly, but it does not need to be, a sub n minus 1. And so for a sub n minus 1 is going to be the previous term. Okay? Because when you write out a sequence whose domain is positive integers, whose domain is 1, 2, 3, 4, then when n is 1, literally that's just the first number in the list. When n is 2, that's just the second number in the list of that sequence of numbers. And the third number and the fourth number for n. So when you see an a sub n is equal to a sub n minus 1, that n minus 1 is just the number just before. Not a sub 5, but a sub 4. If you want to find a sub 4, you're going to use a sub 3 and so on. So set of recursive formulas, a sub 1 usually is a constant. A sub n is found by using some previous number, maybe just specifically a sub n minus 1, and then some other like math. But it's going to be some kind of expression recalling some previous terms, one or multiple terms. Like something called the Fibonacci series uses 2 previous terms, which I think I might do as an example. I thought last period I was going to just rush through like every vocabulary word in this section, and that proved to not be possible. So we might do the Fibonacci series today, see how that goes. So let's say write the set of recursive formulas for the given, I don't know example I'm on anymore, so I'm just going to write example. So let's say we've got 5 for a sub 1 is equal to 5, a sub 2 is equal to 7, a sub 3 is equal to 9. I bet you know what the next one's going to be. A sub 4 is going to be
14.
Funny. 11. What's a sub 5 going to be? 13. I don't need to give you like the world's hardest problem to teach you the fundamental vocabulary, right? We're trying to keep this basic so we can just focus on the vocabulary and the steps. We'll do some harder stuff later. How am I making these numbers? I'm adding 2 to the previous number. So what's a sub 6? Yeah, it's super, super simple. A sub 1 is equal to 5, and any other term in the list is found by taking the, how'd you find a sub 2? You added 2 to a sub 1. How'd you find a sub 3? You added 2 to a sub 2. How do you get from 3 to 2? You subtract 1. So a sub n is equal to a sub n minus 1 plus 2, and that's it. And one of my previous students, long time ago, that graduated and ultimately now he got his engineering degree and works for NASA. I was kind of blown away by this. When they run simulations of how solid rocket booster fuel burns inside of, basically a metal tube, it's done with computers with a set of recursion formulas because computers run so fast. But we're not going to be using supercomputers to run calculations. So the main disadvantage, as easy as this is to come up with for these recursive formulas, is what if I need to find, as my next example, which we're not going to finish, what if I need a sub 100? Well, that's going to be a sub 99 plus 2. Well, I don't have a sub 99. So I have to go find a sub 99 by doing a sub 98 plus 2. And I have to keep doing this until I get back to a sub 6. So if you want the 100th term using a set of recursion formulas, you need the first 99. And when you're not using computers, that's obviously a major disadvantage. So what we want to do as a next example is not write a set of recursive formulas, but write the general term for the given sequence. So I want a single general term that is going to turn an n value of 1 into 5, an n value of 2 into a 7, an n value of 3 into a 9, an n value of 4 into an 11. Like, I want to plug in 4 and get 11. I want to plug in n is 5 and get 13. Now, maybe some of us can just look at this and come up with an answer. Like, has her hand up. What's your general term, ma'am? 2n+3. Okay. So she's coming up with 2n plus 3. So let's see if she's right. 1 times 2? 3. 2 times 2? 4. 3 times 2? 6. 4 times 2? 8. Am I talking to myself? 5 times 2? 10. All of those answers, when we doubled n, how short were we? We were 3 under. So that works out. Awesome. But, and by the way, bless you, 8.2 is going to be learning what an arithmetic sequence is, and this actually is an arithmetic sequence. When you look at this, we are adding by 2, and adding by 2, and so on, and so on. When you see that constant addition that creates the numbers in your list, that is a special type of sequence, one of the two that we're going to learn this chapter called an arithmetic sequence. But we're not there yet, and also I want to teach you some skills that worked for like more than just 2 types of sequences that we're going to learn, which is arithmetic and geometric. So the fact that this is called your first differences are constant, therefore a sub n is going to be a linear function, a linear expression. And that might be a clue to help somebody else besides come up with that 2n plus 3. Oh, I know that I'm going to have an a sub n expression, and there's going to be an n with an exponent of 1. It's going to be, it has to be a linear function. You can kind of come up with this general term by blending the idea that I need one expression that gives me all these terms and more in one step, not consecutively building upon. You can kind of blend the idea of writing a set of recursive formulas in general term at the same time. Like, there is a 5. So you can say a sub n, okay, my first term is 5. So I'm going to say, boom, 5. What am I doing to that 5? I'm adding by 2. Okay, so I'm adding by 2. Well, constantly adding by something, what's constant addition? Multiplication. So, oh, plus 2, plus 2, plus 2, plus 2, plus 2. The plus 2 has to be multiplied by some kind of linear expression. And then you might do some mental math to figure that out. Or, well, this is the second term. From 5, for the second term, how many times did you add 2? Once. For the third term, how many times did you add from the beginning, not building recursively, but starting from the beginning? Ethan? Yeah. Twice. To get to the fourth term, from the beginning, how many times did you add 2? 3 times. Oh, whatever n is, 4, I'm adding 3 times. N is 5, I'm adding 4 times. So the plus 2 is being added an n minus 1 number of times. And thus, and you can leave your answer like this, or you can distribute the 2 and get 5 plus 2n minus 2, or 3 plus 2n. Oh, that was that answer that came up with to begin with. But there's all kinds of ways of processing how to come up with a general term, but it can be actually pretty difficult. This may be not a difficult example, but it can be difficult. So let's do another one. Let's take a look at write the general term for the given sequence. So for this sequence, a sub 1 is equal to 4. A sub 2 is equal to 7. A sub 3 is equal to 12. A sub 4 is going to be, making sure I pick the right one, 19. And A sub 5 is going to be 28. Come up with a general term, please. Give that one a shot. Take a couple minutes. She's like, that was not nearly enough time. By the way, nobody's talking to each other. Come on. What do you think? I highly doubt you got an answer yet. Okay. Can we work through it together? Okay. Let's go off that idea of the first difference that I said was constant. What's the difference? What do you add by to get from 4 to 7? 3. What do you add by to get 7 into 12? And by the way, this is not going to work for all of these sequences. I mean, they really can be quite hard to figure out. To go from 12 to 19? Okay. And then, okay, so these are our first differences, and they are not constant. So that may or may not make them useful. Again, if it's a really, really tough problem, this might be a little bit of a dead end. But it's a process you can try to help you come up with a general term. Now, let's do the subtraction again, though. How do you get from 3 to 5? How about 5 to 7? How about 7 to 9? Okay, these are called your second differences. Second differences are constant. Therefore, a sub n is quadratic, which means it has some kind of n squared. Nice job. With that hint in mind, know that a sub n is going to have some kind of expression with an n squared. Okay, keep playing with the numbers. This time actually talk to each other. Try and come up with a general term. Our second differences are constant. So our a sub n expression or function, wherever you want to call it, must be
Linear. Good one, bud. Quadratic.
okay. So first differences would have a power of 1. If your second differences are constant, you'll have an expression with a power of 2. If you have to go to your third differences, and by the way, none of this has to actually work. You might, if you notice that your third differences are constant, you will have a cubic function. So you have to have an expression because our second differences are constant. You must have an a sub n expression, a general term, that has n squared in it. So 1 squared is, 2 squared is, okay, think about what the answer really is. 3 squared is, 4 squared is,
16.
5 squared is. Now, replay all those answers in your head and look at what the final answer needs to be. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. When you take these values of n and you square it, what's left to do to get these answers in the list? There's your general term.
Boom.
Boom! A sub n is n squared plus 3. Okay, and these, nice job. These, these sequences can have factorials in them, which I haven't reviewed yet with you yet or retaught you. There could be square root functions. There could be all kinds of things going on, but they can be a little bit tricky to figure out. For this example, write a set of recursive formulas for the given series. Not general term, recursive. These are going to be building blocks. So we've got a sub 1 is equal to 1. A sub 2 is equal to 1. A sub 3 is equal to 2. If you've seen this before, don't yell the answer out, because I don't think everybody has. A sub 4 is going to be 3. A sub 5, 5. A sub 6, 8. A sub 7, 13. Okay? I want a pair of recursive formulas that makes that list of, and it's called Fibonacci numbers. This is a list of Fibonacci numbers. It's a Fibonacci sequence, yes. So I need two equations that create this list of numbers, and this would go on forever.
Oh, wait a minute. I see something, but I don't know how it works.
Well, talk it out. You will need this set of recursion. I think I might have misspoke. This set of recursion formulas is not 2 formulas. You'll need 3. Don't ask me. Ask somebody else. I gave you the first number. So the first equation is what? A sub 1 is 1. Not a very interesting equation. And I gave you the second number. So what's the second equation? A sub 2 is 1. And then I started writing down a sub 3, a sub 4, a sub 5, and some people started yelling out answers before I gave it. So what is the last equation? Not sure? Okay, you think you got it. I like that answer. Let's make sure you have it. What's a sub 8? You do have it. It's 21. Okay, so I just asked you for a sub 8, and you correctly told me that it was 21. What two numbers did you add to give me 21? 8 and 13. Okay, so you did 8 plus 13 to give me the correct answer of 21. 8 was what term? A sub 6. And 13 was a sub 7. And how do you get a sub 6? How do you get 6 from 8? You have to subtract 2. So that was a sub 8 minus 2 plus, how do you get 7 from 8? You subtract 1. So that was a sub 8 minus 1. So in general, you found a sub 8 by doing a sub 8 minus 2 plus a sub 8 minus 1. So what if I asked for a sub 10? Or a sub n? Because I just asked for the 8th number. But you really worked with a sub 6 or a sub 8 minus 2 or a sub n. What are we doing with an n down here? What'd you do with that n? Minus 2. And then you added it. Well, wait a minute. You took the 8, the n, and you subtracted 1. So a sub n is a sub n minus 2 plus a sub n minus 1. And that is your set of 3 recursion formulas working together that create this Fibonacci series that just goes on forever. Nice job. Woo! Let's go. We good?
Great.
All right. I'm excited. Woo! I'm so excited. I want to talk about factorials. Why do I want to talk about factorials? What's the math symbol for factorials? An exclamation mark. Thingy down. Okay, so what is 4 factorial?
24.
You're so annoying. 4 times 3 times 2 times 1. And yes, that does happen to come out to be 24. Which means that, now, I know there's an excellent explanation for this. However, don't know what it is right off the top of my head, and we're starting to run out of time. 0 factorial, by definition, is 1. There is a really good explanation as to why that's defined to be 1, and right off the top of my head, I don't know what it is. I can easily explain why anything to the 0 power is 1 using properties of exponents, but 0 factorial is defined to be 1. So 4 factorial is 4 times 3 times 2 times 1, which is 24. Okay, 0 factorial is defined to be 1. I'll look that up and tell you tomorrow. But what is the expansion of n factorial? If 4 factorial is 4 times 3 times 2 times 1, and by the way, before we expand this out, what do you call numbers that are being multiplied together?
Products.
Wrong. This 24 is the product of 4 times 3 times 2 times 1, but individually, the 4, the 3, the 2, and the 1 are factors. Thank you, Jim. If these were plus signs and not multiplication symbols, the 4, 3, and 2, and 1 would be what? What do you add? Starts with a T. You add.
Terms.
So thank you. Thank you. You add terms and you multiply factors. Okay. I mean, I've been using that vocabulary all year, but last period kind of like threw me for a loop there. So n factorial, or n, throw your marker, n, is n times, how'd you get 3 from 4?
Subtract 1.
Subtract 1, n minus 1, times, how do you get 2 from 4? Subtract 2. So n factorial is n times n minus 1 times n minus 2, but we don't know what n is. If n is 3, it's 3 times 2 times 1, and you're done. But if n is 100 factorial, which I don't even know what n is, but if it were 100 factorials, I'd have to write 100 factors. So n factorial, without you knowing how many factors there will be, how you expand that in algebra notation is n times n minus 1 times n minus 2. And when do you stop factorials? When you list it, when you subtract 1 until you get to 1. So a little dot, 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 3, 2, 1. And the little dot, dot, dot opens the door to maybe there's 3 terms, 6 terms, 1,000 terms, I don't know. No, factors, factors.
I don't get that last part. Why 3, 2, 1?
What's 4 factorial? Is it 4 times 3?
No.
Is it 4 times 3 times 2? Technically, the answer is sort of technically yes. But you stop, factorials expand, the list of products expands till you get to 1, and then you stop.
Could you stop it at 1 since everything times itself is?
And by def, go to 1. So,
Oh, I got it. Never mind.
okay. So, n factorial as an expansion is an unknown value. If it was 4, it's 4, 3, 2, 1. If it's 5, it's 5, 4, 3, 2, 1. If it's 10, I don't want to say that many factors. If it's n times n minus 1, like 3 minus 1, like 3 comes from 4 minus 1. N minus 2, like 2 comes from 4 minus 2. But then that n minus 1, n minus 2, n minus 3, n minus 4, it doesn't matter if, I mean, I can keep saying that, but I don't know what n is. So a little dot, 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 the expansion stops at 1. So 3, 2, 1. And that idea of expanding n factorial as an algebraic expression will allow you, yes, time is passing, you can stop looking at the clock, to do n plus 2 factorial over n factorial. What does that expand out to or simplify to? Last example, because we are obviously running out of time. What would be the expansion and simplification of n plus 2 factorial over n factorial? And I'd give you time to think, but if I do that, the announcements are going to come on. So what's n plus 2 factorial? Well, it's n plus 2. And then how'd you get to 3? Subtracted 1, so subtract 1. N plus 1, subtract 1. N, subtract 1.
Oh, sick.
Subtract 1, what's the next one? N minus 1, it's not the word sick. And that continues until you get to 1. And how do you expand? It is kind of sick. How do you expand n factorial? N, and take 1 off, And if you feel the need, take another one off. But what's going to happen? I don't know what n is. I don't know if I have 3, 10, or 100 factors, but I know I'm going to continue this until I get to 1. And what do common factors do? Cancel out. Anything divided by itself is 1. So the final simplification is n plus 2 factorial, an infinite number of factors over an infinite number of factors is going to reduce to be n plus 2 times n plus 1. And that's how you reduce factorial expressions. If you want to write less in your expansion, which is a really good idea, you've got n plus 2 times n plus 1. Sit down for a second. You might actually want to hear this. N plus 2 times n plus 1, the next one is n, but, oh, wait a minute. I know I'm doing factorials, and I know I'm going to go down forever, but I have that match of n, so you can write n factorial. And then have that be over n factorial, and then cancel that out. It's the same answer. Yeah. Have a good one.